In this video, I'm going to work through a few questions from homework number 12 in our college algebra class. And these are problem numbers 17 through 20, number 30, and 31. I've been asked a few questions on these this week, so I thought I'd record a video to go through them. Now, your question number 17 is going to look similar to this. It may not be identical, but it is similar. We have two functions that are rational, and we need to find the composite functions and then state the domain of each. So I don't think I'm going to work through all four parts, but I'll start with, say, part A. If our job is to compose f with g, that means to compose f with g at x. And when we compose functions, that means to take this outer function, the one on the left is our outer, and replace the argument of the outer function with our inner function, g of x. So in a sense, what we're doing is we're writing or building a template based on function f. Function f is going to be something minus 4 in this case, because I'm looking at this numerator, divided by something plus 7. And the something is no longer x by itself, but it ends up being the entire function g of x. So I have x plus 5 over x minus 8, and another x plus 5 over x minus 8. And in a sense, this would be okay as a final answer. However, the instructions do specify that we must simplify our answer and factor completely. So in order to do that, since this is a complex rational expression, we should really find common denominators for this numerator group and the denominator group, so that we essentially get one fraction in the numerator divided by another fraction in the denominator, and then we could simplify from there. So in order to make that happen, I'm just going to simply multiply both this 4 and this 7 by an appropriate form of the number 1. And the appropriate form here is going to be x minus 8 over x minus 8. So clearly x minus 8 over x minus 8 is equal to 1, and 4 times 1 is still 4. But by multiplying by x minus 8 over x minus 8, that's going to change the way the 4 and the 7 look, so that we can have a common denominator and combine the fractions in the numerator and the fractions in the denominator. So in the numerator, we still have x plus 5 over x minus 8, and from that we're subtracting 4x minus 32 over x minus 8. And I'm getting that 4x minus 32 because I'm distributing 4 into x and 4 into negative 8. Now, I personally think that it's helpful to distribute the negative sign as well. So if we had a negative 4 times x, this changes the sign to a plus here and a minus here, but a plus here as well. And that's going to make combining like terms just a little bit easier. In the denominator, we have x plus 5 over x minus 8. And to that, we will add 7x minus 56 over x minus 8. And now both the numerator and the denominator have a denominator within as x minus 8. And the numerator of the numerator, this is where it gets a little bit easier. X take away 4 is negative 3x, and 5 plus 32 is 37. And in the denominator, x plus 7x is 8x, and 5 plus negative 56 is negative 51. Now, if the denominators within each component of this fraction were different, then I would definitely recommend rewriting this as a product instead of a quotient. And we would have negative 3x plus 37 over x minus 8, because that's our numerator. And when we divide by another fraction, that's essentially equivalent to multiplying by the reciprocal. And the reciprocal of this denominator is x minus 8 divided by 8x minus 51. And hopefully you notice pretty quickly that this x minus 8 and this x minus 8, when the two fractions multiply together, will cancel. They'll factor out with one another, and we're now left with negative 3x plus 37 over 8x minus 51. And there's your simplified result. Now, provided that you encountered a situation like this where the denominator of both the numerator's fraction and the denominator's fraction of the complex fraction, if those two are the same, then you could essentially skip this middle step, because we would always recognize that the denominator here and here are going to factor with one another and cancel each other out, and they essentially disappear. So if that is the case for you, then by all means skip from here straight to this answer, and that would be just fine. Now, as far as the domain goes, we have to consider that four-step process that was introduced in the videos this week, or this past week, depending on when you're watching this video. I believe I first walked through this in Unit 4, Part 1, Lesson 2. And here's what those notes would have looked like. Here's that process for finding the domain of a composite function. We either identify the domain or the restriction of our inner function, then we do the same for our outer function. We don't want to allow the result from our inner function to equal the restriction of the outer function, and so we find where that occurs, and then to report our answer, we combine steps 1 and 3. So this should be labeled 1, 2, 3, 4. So whatever answers we got in step 1, whatever answers we got in step 3, those are the results for the domain of the composite function. So in this particular case, we want to find the domain restriction of the inner function. So our inner function was this guy, g of x. So when is this going to be a problem? Well, in class, I had mentioned how you can think of this as, when is there a restriction, or for what values is this function acceptable? And in this particular case, I think it's easier to think about the restriction, because I can really plug in any number for x here. When we're talking about the domain, we're trying to identify what numbers can be used, what real numbers can be used in this expression to generate a real number result. And any number can be plugged in for x here except for positive 8. And the reason why we don't like using positive 8 is because if x was replaced with the number 8, well, that doesn't really cause a problem in our numerator. 8 plus 5, that's going to produce a real number result. But 8 minus 8 in the denominator produces a 0, and ultimately we would be left with 13 divided by 0. And we can't simplify that in our real number system. So therefore we would say that 8 is an exclusion for the domain. Any other value would be perfectly fine. If I had used a 1 in either case, I would eventually calculate a real number result. If I used the number 2, 3, 10, you name it, any other real number when placed into this expression will generate a real number result except for the value 8. And so that's why I would say our restriction is the number 8. For step 2, we would do the same thing, but look at our outer function. Now our outer function, and I'll label this, by the way, this was g of x. Our outer function was f of x, and that's equal to x minus 4 over x plus 7, x minus 4 over x minus 7, plus 7. So the domain restriction here, in much the same way, since we're dealing with a fraction, is that we don't want x to be equal to negative 7. And this is for much the same reasons as before. If x was ever allowed to be equal to negative 7, then that would produce a 0 in the denominator, which we would like to avoid. And I probably should note that x is not allowed to equal negative 7. That's our restriction. So for part 3, we don't want our inner function, x plus 5 divided by x minus 8, to ever equal this restriction on the outside. Because again, this x plus 5 over x minus 8 was placed inside of our outer function. And if the result from this calculation, if that result ever equaled negative 7, well, this result that calculate it to -7 would end up creating a -7 plus 7 and another 0 in the denominator. So we want to avoid this situation at all cost, and so we identify this as a restriction to our domain as well. So I'm going to use regular old algebra to solve this. I'm going to multiply both sides by x minus 8. So we now have x plus 5 equals -7 times x minus 8. And it'll be worthwhile to distribute here. So we'll call this -7x plus 56. Now I might add 7x to both sides to obtain 8x and subtract 5 from both sides to obtain 51. And x would then be equal to 51 over 8. Now in reality, we were saying that we didn't want x plus 5 over x minus 8 to equal -7, so we want them to not be equal to one another. So I can come back now and just change all of these to not equal signs, or inequalities, and I'm okay with that as a result. When we report our final answer, the domain restrictions are that x may not be equal to number 1, so 8, and x may not be equal to the result that we got in number 3. As it turns out, if I were to substitute the number -7, which wasn't appropriate for the outer function, if I were to substitute the number 7 into this expression, then we would be able to calculate a real number result. So it's not that detrimental anymore once we have the composite function, or composite function. And so that's the process that I would go through for each of the 4 parts on question number 17. So I hope that provides a little bit of clarity and gives you an opportunity to try these on your own. Let's bring in number 18 now. So with number 18, we start talking about a real-world situation in which we will compose 2 functions. And we're told that the surface area of a hot air balloon is given to us by this particular equation, and the equation is dependent upon the radius of the balloon. So if I knew what the radius was of the balloon, now I can calculate the surface area by using this particular function. Well, as it turns out, it's kind of difficult to measure the radius of the balloon while it's being inflated. But what we do know is that the radius of the balloon, based on the amount of time that passes, follows this particular equation. So I can easily measure with a stopwatch the amount of time that's passed since I've started filling the balloon. And if I know how much time has passed, I can calculate the radius. And once I have the radius, I can then calculate the surface area of the balloon. So the question becomes, is it possible to write a single expression or equation that models the surface area of the balloon as a function of time instead of as a function of radius? And of course that's possible. S of t, the surface area based on time, would simply be the result of the surface area of the radius, where the radius was dependent upon time. So we're going to take this radius function and put it in place of the argument for our surface area. Now our surface area required 4 pi times some radius squared, and as it turns out, our radius was 2/7 of t cubed. And this expression here on the right-hand side would in fact model the surface area based on time. If I knew how much time had passed, I can substitute that time value in for t, execute this expression on the right-hand side, and we would know the surface area of the balloon. But the instructions do ask us to simplify and to report our answer using pi as needed, and fractions as well. So there's no need to use a calculator here. If we imagine the number 4 pi as 4 pi over 1, and we're multiplying by 2/7 t cubed quantity squared. Since the 2/7 is being multiplied by t cubed, then it would be appropriate for us to distribute this power of 2 into this grouping symbol. We can only do that distribution if there's a series of multiplications inside that grouping symbol. If there was an addition sign here, that wouldn't work. Instead, we would write this expression twice and FOIL it. So we still have 4 pi over 1. You'll see why that's written as a fraction in just a moment. If the number 2/7 is squared, that means we square both the numerator and the denominator. 2/7 times 2/7 is 4/49. And t cubed squared becomes t to the 6th power. The power to a power rule requires us to multiply those two exponents. Now, because I have two fractions that multiply together, I can multiply numerators with numerators. So we've got 16 pi, denominators with denominators, over 49 times t to the 6th power. And this is our surface area formula based on time. If you follow these suggestions from MathXL, they may lead you to write the result like this: 16 over 49 times pi times t to the 6th power, and that would be acceptable as well. 16 pi over 49 is exactly the same as 16 over 49 times pi. Let's take a look at number 19. In a somewhat similar scenario, we have a price equation where the price that we establish for the cost of an object, or I'm sorry, the price that we would charge for selling a good is equal to the demand, where X represents the quantity within that demand function. And similarly, the cost to produce a certain number of goods is related by this equation. So the cost based on the quantity is this equation down here, and the price based on quantity is this expression here. So our goal is to find the cost as a function of price P, but the problem that we have is that the cost function was written in terms of X, our demand. And that's not too much of a challenge, because what we can do here is we know how the price is going to relate to the demand, the quantity demanded. We could simply isolate X in terms of P, and then we can make the substitution. So if we were to take this equation, P equals negative 1/6 X plus 700, we could subtract 700 from both sides, then multiply by negative 6 to eliminate this fraction, and now we have negative 6 times P minus 700 equals X, or in other words, X by itself is equal to negative 6P plus 4,200. Now we have the relationship between price and demand, and this is pretty typical. As price fluctuates, that may affect our demand, how many products would be sold based on the price of that product. Now, when we evaluate our cost based on price, let's write it this way, give ourselves some room here. We have the square root of something, the square root of X divided by 100, made that fraction bar too big, square root of X divided by 100 plus 800. As it turns out, the X now is not just X by itself, but it's this entire expression. So we'll substitute negative 6P plus 4,200 in terms of C. And so I think this would be a pretty good cost formula, but in the event that they're asking for some restriction on the domain, and by the way, we would say, since our variable here is P, that this is the cost based on price, P, the price that we sell the goods for. Well, in this particular situation, what we don't want to see are negative numbers inside of a radical. As when we take the square root of something, we can take the square root of any real number and obtain a result as long as that real number is either 0 or greater, if it's a positive number or equal to 0. So when I'm looking for a restriction on a problem that contains a square root, I want to make sure that negative 6P plus 4,200 is greater than 0. I got to make sure that that's positive. So what I'll probably do is take this negative 6P and add it to both sides, and so now I've got 4,200 must be greater than 6P. than when I divide both sides by 6. And be careful here, you don't want to go changing your signs just yet. We know that p has to be less than 700. So we can switch both sides now. P must be less than 700. Although I think I misspoke. We can take the square root of 0. So it's okay if I say that this expression is greater than or equal to 0. And so p must be less than or equal to 700. Now, additionally, we don't want to give the product away, so we don't want to let the price value, or I'm sorry, the price that we establish for this good or service to be any less than 0 itself. So in theory, we could have a price set to 0, but we don't want to allow our price to go less than that. Then we'd be losing money. So I believe this would be the result that MathXL is looking for when we talk about domain restrictions for the cost function. An argument can be made about changing this to a less than symbol, but I think for this case, we'll say that a less than or equal to would be appropriate. And moving on to number 20, the last in this little group. The volume of a right circular cylinder of height h and radius r is given to us by this formula. The height, this is kind of interesting, the height is going to be 4 times whatever the radius is. Can we express the volume v as a function of r? Right now, if I needed to calculate the volume of this right cylinder, I would have to provide both an r value and an h value. I'd have to provide 2 measurements in order to calculate this particular volume. And while that's not too challenging, it's always nice if we can establish a function based on 1 variable instead of 2. And this expression here telling us that the height is required to be 4 times the radius, this expression helps us perform that substitution. We again essentially perform a composite function here. So wherever we see an h, we're going to substitute or compose this volume function with this height function. And now we're dealing with the volume based on h and h only. Sorry, volume based on r and r only to be pi times radius squared times 4r, since the height is essentially 4 times the radius. If we were to simplify this, well, we've got pi times radius squared times 4 times r. There's no need for the parentheses. When we combine like terms with multiplication, we end up with 4 pi times r cubed. And the volume for this particular cylinder, given those restrictions, is 4 pi times radius cubed. And there's no mention of domain restriction in this problem, but of course we should always be mindful of that. As far as our domain goes, I think we would only want to produce cylinders whose radius is greater than 0. If the radius was equal to 0, we would no longer have a cylinder, and if it was less than 0, well, same sort of thing. We can't have a cylinder whose radius is a negative measurement. Now for problem number 31, that's this guy here. This is number 30. We actually need to reference the third video from last week. So Unit 4, Part 1, Lesson 3. That's where we talk more about inverses. And so we can only find an inverse if a function is 1 to 1, and we're being told that this function is 1 to 1 as long as we use x values that are greater than 0. So we need to find the inverse and check the answer. And the method that I used to establish inverses is I changed the f of x notation back to the letter y. So we've got y equals x squared minus 3 over 5x squared. And then we switch the x and the y. So we've got an x equals y squared minus 3 over 5 times y squared. The reason why we do that is because an inverse is the opposite. Inverse is an opposite function, and opposite, I use that phrase loosely here. It's technically the opposite of this equation, and The opposite equation will undo this equation, or will help us solve this equation without having to use algebra each and every time. So since I'm looking for the opposite of this given equation, I'm just simply switching the x's and the y's and considering those as opposites to one another. So now, after I've rewritten the problem and switched the x and the y, I just need to solve and isolate this y squared. So here's where we've got to use a fair bit of algebra and get creative with it, but I think it becomes a little bit easier the more you practice and the more examples you see. Now the first thing that I'm going to do is I'm going to eliminate this fraction. I don't particularly like working with them, so I'm going to multiply both sides by 5y squared. In doing so, I'm going to end up with a 5x times y squared if I reorder this using the commutative property of multiplication. And on the right side, I have y squared minus 3. Now another trick that's helpful when we've got several examples of terms with y in them is to get all of those terms on one side of the equation. So I'm going to subtract y squared from both sides of the equation, and that gives me an expression equal to negative 3. And the reason why I've done that is because this y squared is now going to act as a factor that's common to this first term and the second term separated by the subtraction sign. So if y squared is acting as a common factor, then y squared times 5x minus 1 is equal to negative 3. And when we divide both sides by 5x minus 1, we have y squared equals negative 3 divided by 5x minus 1. And now we can take a square root of both sides of the equation, and we have y equal to plus or minus the square root of negative 3 over 5x minus 1. Now here's where our domain restriction is going to be helpful to us. Originally we were told that x must be greater than 0 in this case. And that's in our original equation, our original function. Well, recall that we switched x's and y's, so when we get to this point here, we must say that y must be greater than 0, because again, we're talking about opposites here. We reversed the x and the y, so when x was greater than 0 in the original, y must be greater than 0 in the inverse. And by knowing that y must be greater than 0, y must be positive, I can eliminate this minus sign in this square root symbol. So to be perfectly appropriate, we would include both the plus and minus sign when we apply the square root symbol, but because of our domain and range restrictions, we're dealing only with positive y values. And the other point that I want to make and remind you of here is that this y value at the beginning is not the same as this y value at the end. These two are different from one another. These are not the same. Okay, so now, usually within a particular problem, all y values and all x values are equivalent to one another, but not in this case, because we did arbitrarily switch the x and the y values along the way. This y value at the beginning represented f of x, whereas this y value at the end actually represents the inverse of f of x. And so by process of switching those components around, we've actually established the inverse function in terms of y. And so if I were reporting this answer at the end, I would say that f inverse of x, I should say, is equal to the square root of negative 3 over 5x minus 1. Whereas f of x was equal to this. Now the process to check this answer is a bit lengthy, and I'm not going to complete that in this video, but I'll remind you that in order to check your answer, you must compose the function and its inverse in both directions. So compose f with f inverse and do the math to simplify that expression, and your goal is to see that it ends up equaling x. We would have to do the same in the opposite direction, and we would take the inverse function and compose it with the original function, f of x, and simplify that expression. And again, we expect this answer to be x as well. If after simplifying these compositions and both end up equaling x, then we have verified that this function indeed was the inverse of this function. So it's a bit of a tedious approach, a tedious process, but it is required in order to complete this particular question. Now, MathXL may not require you to show all of your work for that step, but should we see that question on a test or exam, you will have to show your work for both checks. And I'm taking a look at my watch here. I've got 3 minutes before another class comes in, so I'm not going to be able to finish this particular example, but I will note that an example virtually identical to this was completed in the video Unit 4, Part 1, Lesson 4, where we can rewrite a function, in this case the amount of distance that it takes for a car to stop based on a particular rate of speed, and rewrite it in terms of another value. So that's particularly helpful, as is indicated here, when it's not always helpful to find the or solve or use algebra to solve a particular problem each time. Sometimes it's helpful to have an entire inverse equation to help us solve a particular scenario. So if you go back to Unit 4, Part 1, Lesson 4, the problem number 89 talks about this particular style of question, and I'm certain my discussion there would have been similar in this video, and I think that should be sufficient to help you through this particular question. If you do have more concerns or questions, send me another email, or we'll talk to each other in class next time we meet. So thanks for watching.